In this video, we are going to look at thermodynamics and kinetics of leaching. And our focus will be on how we can construct stability diagram. The stability diagram shows the area of stability. Also, it shows the predominant areas of various metal compounds and species. So, one may ask what are the importance of constructing a stability diagram. So the stability diagram can be used to design the solution, which is in this case the leaching or the reaction path without any experimentation. And also it relates a condition to equilibrium species and provide only reagents for dominant species. So we are going to take this example, and per this example, we're going to learn how we can construct the stability diagram systematically. Consider M2O/M2 plus system. You should plot the PE against the pH, and also should plot EH against the pH. So in this case, we're doing that to enable us to one, construct the stability diagram. Let's go on. So first, we need to know some basics before we start this. Let's learn some basics before we constructing this. So the first basic is that we should know that pH is equal to negative log of hydrogen ions. And the second one is we should know that PE is equal to negative log of E minus. And the third one is the relationship between the PE and the EH is that PE is equal to EH over 0.059. I hope you understood that. So we are going to take these three things, which is going to enable us to construct a stability diagram. So in that case, let's move on. Now, so we're constructing the stability diagram. We first need to balance the equation given to us for the system. So we're balancing the equation for the system. We will know that M2O is giving us M2 plus. And in this case, we are using it in what? Balancing in acidic medium, whereby we know that where we have oxygen, look at the moles of oxygen and add water to the other side. That's the product side. So in that case, we have what? One molecule of oxygen here. So in that case, we're going to add one molecule of water here. Now we can know that here we have two molecules of M, so we are going to add 2 here, 2. Now still the equation is not balanced, because in that case, when you add water here, you're supposed to add hydrogen ion here, and we are adding hydrogen ion, and in that case we have 2 molecules of hydrogen ion, 2 moles of hydrogen ions here. We will bring 2. Now we also check whether the system is still balanced. We know that with the ions we have 2, and here we have 4, so that means that we need to balance with what? 2 what? Sure. Try to be balanced. Balancing the equation is the key to this. So if you cannot balance it, you need to balance it very well before you continue. Now after balancing, then we move on. Let's move on. Now balancing the equation, then we move on to we having some relationship here. In this construction, we are going to use the forward reaction, whereby the forward reaction condition states that K should be greater than or equal to Q. Let's explain this variables. With K represents the equilibrium constant, and the Q is the reaction quotient. And when we talk about the reaction quotient, it measures the relative amount of product and reactants present in a reaction at a given time, and also it is used to predict the direction of the reaction to reach equilibrium. So in that case, let's look at this. So Q is going to give you the product, the concentration of the product all over the concentration of the reactant. And then K is also going to give you a concentration of the product. In that case, that is in equilibrium all over the concentration of the reactant, which is also in equilibrium. So let's get going. So after we having this, developing this, we therefore come in and say that then our Q will be equal to, which one is our product? These are our products, right? These are our products. In this case, we have M2 plus exponent the number of moles times our water, then times our electron exponent 2 all over our reactant, which is M2O concentration, then times our hydrogen ion, which is 2 plus exponent 2. So in that case, we should note that in this case, all solids and liquids species is to 1. So in this case, this will tend to 1, and this will tend to 1. It's very important. That is, the activity of solids and liquids in this reaction tends to 1. So in that case, our Q then tends to our M2 plus then times our electron then over our hydrogen ion 2. Hope you had that. Let's move on. So after doing that correctly, what to do now is that you can also find the K, and in that case the K also will be the same, but that to be in equilibrium, right? Yeah. Now we need to find the log of Q. So for us to find the log of Q, for constructing of that, we need to find the log of Q. This is for forward reaction. For forward reaction to take place, we are using forward reaction. That means that we are going to get more of the product, right? For forward reaction condition. And we need to find the logarithm of this, log of this. So we find the log of that. This condition will change and change to log A be greater than or equal to log Q. So let's find log Q. So with log Q, our log Q will be equal to what? With the logarithmic rule, we know that this is going to give you 2 log M2 plus, then plus 2 log electron, then minus 2 log hydrogen, the concentration of hydrogen ion. I hope you understood that, because you've changed it to logarithm, and if it's over it's minus, and if it's multiplication it's plus. So in that case, after you've done that, let's do some substitution. We are going to do the substitution. We are going to substitute this into this, right? So when you do that substitution, let's move on to the substitution. With that substitution, when you do that, we're going to have that our log A will be greater than or equal to our log Q, giving you 2 log M2 plus, then plus 2 log E minus 2 log hydrogen ion. As we established that negative log of hydrogen ion is pH, and negative log of electron ion is what? That's the E minus is what? P, which is the potential. So in that case, log K would then change to 2 log M2 plus, and this will be minus bracket open 2 log E minus, then we close minus 2 log hydrogen ion. We want to get our what? Our PE, then negative will give you positive, right? So there's nothing that we've done here. We just want to get our PE. So when you do that correctly, our log K is going to give you 2 log M2 plus minus our 2 PE, then plus 2 pH, because negative log of that will give you pH. So it plus. Now after getting this, then we are going to use this information to plot or to draw our what stability diagram. Now we using that table to draw our stability diagram, let's look at something here. If you can see, this will be like we are plotting. First we are plotting PE against pH. So we plotting PE against pH, we try making our PE the subject. So in that case our PE will be equal to 2PE will be equal to greater than or equal to, so we send the log to this log k to that. We're going to have our 2pH then plus 2 log m2 plus then minus log k. Now after getting, we need to reduce it. So when you divide 2 by 2, we are going to have that our PE will greater than or equal to pH then plus log m2 plus then minus 0.5 log k. So this is the information that we have here. This is what we are going to use to construct our stability diagram. So let's do that correctly. So for our stability diagram, we know that this is forward reaction, right? And for the forward reaction, more of the product is formed. Now this look like equation of a line, right? So we have y is equal to mx plus c. Now these represent the constant, and this is the mx. So the gradient will be a number in front of that. So this represent the mx and this represent the constant. So let's notice something. If the gradient is negative, you know that the line will change. If it's positive, you know that the line will change. So since it's a forward reaction here, this sign has no change and it's a forward reaction, we are going to get more of the product. So when drawing the stability diagram, we have our box here and we are plotting our PE against our pH. Now we know that with that, since it's positive, our line will move this way. Since it's positive, right? Since it's positive, our line will move this way. Yeah, our line will move this way. And the predominant species, since it's acting, it's still in a forward reaction, we are going to get more of the product. So that means that the predominant species will be our product, which is M2 plus, and our reactant will come down, which is M2. So we've constructed the stability diagram. In this case, we've established that this is the predominant area. Yes, we are plotting our PE against pH, and we've done that. Now let me explain something to you. Imagine that we had, let me summarize this. We have pH is this pH plus our C, which is in this case the constant. What if, let's go to our next page and let's see something. What if, right, we had our answer one was PE is greater than or equal to pH and we had our constant, right? What if we had the answer to be PE is greater than or equal to negative pH plus C? In this case, when this is negative, it means that our gradient is negative. We are going to have our PE against our pH. But in this case, since it's negative, the line will move from here to this side. And this is still forward reaction. We have our product here forming and our reactant here. Let's look at another example. What if we had it to be, so this is the first one, which was the answer, and this is, I'm trying to explain it to you in certain conditions. So what if we had our PE to be less than or equal to pH plus C? In this case, it means that our forward reaction has changed to backward reaction, so therefore we are going to form more of the reactant. So you drawing the Pube diagram, which is the stability diagram, we are going to have that this will be our PE and this will be our pH. But in that case, the line will still be positive because our gradient is positive. We'll move this way, but our predominant species will be the reactant, which is M2O, and this will be this because the sign has changed and is moving to the backward reaction, whereby more product to be, but more reactant to be formed. This is it. So it's moving to the reactant side. So we get this. Let's look at another one. What if then we move to the next one. What if we had our answer to be pH is less than or equal to negative pH plus C? We had our P is less than or equal to negative pH plus C. In that case, you drawing your stability diagram, we're going to have this one to be like this. And this will be our pH. And this will be our PE. And since this is negative, it means that the graph will move here. The gradient is going to move here from this side to this, right? Move here. And then since it's going to it's backward reaction, be careful. We have certain conditions that you should look at. There's the first condition, second condition, the third condition, and the fourth condition. So that also will give you mark for you drawing our stability diagram. Let's move on to the question number 2. What they ask us to draw is, you should draw, first was PE against pH. Now we are drawing EH against pH. Now we established that our PE was a forward reaction greater or equal to our pH plus our constant. We are using C as our constant, which is, we had 0.5, negative 0.5 K plus 2 log M2 plus. So in that case, when you are going to, we've established that PE is equal to EH over what? 0.059. So in that case, you generating it from there, you're going to have that our EH will be greater or equal to 0.0591 EH plus 0.059 C, right? In that case, still we had a constant to be, it's going to give you this 0.0591 EH plus our C. But you know that our C, we established our C is what? 2 log M2 plus minus 0.5 log E, and we are representing as what? Our C here. Now after this, we are supposed to draw our way diagram, which is the stability diagram. In that case, when you are drawing it, you do it like this. We have our EH, and it's the same condition. If this is forward reaction, that means that we have more of the product being formed, and this also, the gradient is positive. That means that the line is going to move here, but it's moving it somewhere like this, right? And then we have our dominant species to be M2 plus, and this will be M2O.